For some reason.
So yeah, so the next and last speaker is Subhasree Patro, who is a PhD student at CWI, paid for by Bosch, I guess by the Bosch Foundation, not directly by the company. And this will be a talk about some complexity theoretic aspects of quantum computing. Please, Subha, go ahead.
Hi, everyone. I'm Subhasree Patro, and I'm working on this project called Quantum Fine-Grained Complexity. It's a joint work with Harry Baumann, Florian Spielmann, and Bruno Love. This term, I hope you all can see my cursor. If not, just tell me. So this term,
we can see it.
Okay, it's not unfamiliar anymore. But these other terms, I will be talking in my slides, and it'll be clear. So no worries. Okay. Yeah. Following footsteps of Harry, I also decided to have a little thought experiment for all of you. Okay. Okay. Consider there's this point A somewhere in Netherlands and this point B somewhere in India, and we have the sailboat, and we want to travel from point A to point B. And what we would like is minimum sail distance. We don't want to take too long. We don't want to travel too long. So we want to have this, we want to know what is the minimum sail distance between, say, point A and B. So one possible way to see is to find a particular route first. Let's say we have this route X, and we know that now the minimum sail distance between A and B is kind of upper bounded by the length of this route X. Okay, but soon enough, people will realize that there's another better route which goes through this Suez Canal, and the minimum sail distance now has, we know a little more about the minimum sail distance. What additionally we now know is that it is upper bounded by this length of route Y, which is much smaller than this dx. Okay, but how do we know when to stop? How do we know when not to look for better routes? So this is where the lower bounds come into picture. And now let's look at this. So if we want to traverse from A to B and we have the sailboat, uh, one of the we cannot go better than the geodesic distance between A and B. And by geodesic, I mean the straight line that kind of goes along the surface of the Earth. Okay. Now this becomes the lower bound for this problem. Okay. Now the reason why I even brought this topic is to kind of point to all of you that the way we improve the upper bounds is doesn't follow the same reasoning the way we get these lower bounds. Okay, now let's continue with another little thought experiment. Now imagine we didn't have the sailboat, but we had this really healthy mole that can dig its way through the earth. Okay, and the problem is still the same, that the mole wants to traverse from A to B, but now it's not on a sailboat, but he or she is going to just dig her way through. So now the minimum distance for the mole is going to be upper bounded by this length of this geodesic route. But given that it has these digging capabilities, and I'm assuming that the mole is very heat resistant, it can actually, possibly go through this dig its way through and go through this tunnel between A to B, kind of giving this lower bound as the Euclidean distance and upper bound as this geodesic distance. Okay. Now, why am I talking about all this? So one of the take-home message from here is, when you have different computational models, you could have different upper bound and lower bounds for the same problem. And in this example before I gave, the sailboat was kind of like one computation model and the mole was like the other. And the mole clearly had a lot more power than the sailboat. And second take-home message from this is to show that, the techniques that we use to give a low bound, like the reasoning that we followed to give the low bound, was very different from the way we were getting the upper bounds, right? So this is why I was talking about this thought experiment. Now let's look at some more slightly boring things. That is the upper bounds and lower bounds in complexity theory. So what do we have in our setup? We have some computational problem A, and we would like to know how much time it takes to solve problem A. Okay. Now I'm not talking about quantum here. I'm just talking about, we have some computational model and we have this problem and we want to know how much time it takes to solve this problem A on a particular computational model. Okay. So, so what is upper bound? The upper bounds are like the best known algorithm that is known at that point of time to solve problem A. And what is lower bound? Lower bound kind of indicates like uh, time required by any algorithm to solve this problem A. Okay. Now, when the upper bound and the lower bound finally match, that is what is the complexity of this problem. Now, the sad part is that for many problems, we do not know this complexity. We don't even know the classical complexity. So, let alone the quantum one. Okay? But the reason why we are looking at this upper bound and lower bound is because right now we would like to assess how useful quantum computers are for us. I mean, so much money is coming into it. So we really need to know for which problems quantum computers can help and which problem quantum computers cannot help. And we saw in Harry's slides also that quantum computers are more powerful computational model than classical computers, right? But does that mean it can, speed up every problem? Not really. So, but how do we assert that? How do we prove that it cannot solve, every problem as fast as the other problems? So for now, what we have is a set of examples, like say for problems like integer factorization and discrete log, we have quantum algorithms which are exponentially faster than the existing classical ones. And for problems like finding triangle, some geometry problems, three sum, CNF-SAT, like all these problems in Brown, we have quantum algorithms that are polynomially, like some of them are quadratically, polynomially faster than classical algorithms. But sadly, for these problems like longest common sequence, edit distance, preset distance, and this parity CNF SAT, actually there are no quantum speedups that we can see. And the work in my project that I'm doing right now is to kind of give evidence as to why we are not able to find better algorithms for say LCS or edit distance, or and some more work that we are doing is to kind of see that maybe for some problems like geometry problems and all, we cannot have more than polynomial speed up, quantum speed up. And so this is what the project is about. Okay. And yeah, so my our contribution is going to be that we give low bounds for some of these computational problems. And the technique that we used is called fine grained reduction. And as promised, this was my second part of the title, like second part of my project title. So I'm going to talk about that now. Um, Let me first give you an example of reduction. So imagine we have a computational problem where we have two numbers and we want to just know their product. And say we have another computational problem where we have like we input one number and we have to compute the square of the number. Now, clearly, if I had an algorithm, say someone asked me to solve problem B, and I don't know how to solve it, but I have an algorithm that solves problem A. So clearly, I can use the algorithm of problem A and solve problem B by just putting A as A and B also as A and get the answer. And for this particular example, the other direction is also pretty nice, and that is because uh, we have this formula that we all learn in high school, where we can actually use this algorithm that is of problem B that can, compute a square of a number, and we could just compute the square of A plus B, then square of A and square of B, and then compute the whole answer to A to B. And again, the reason I'm trying to talk about this reduction idea is that, see, uh, the both these problem this relation that we have got here kind of establishes that both these problems are computationally equivalent. What do I mean by that? What I mean is, if say I had a really fast algorithm to solve problem B, then I could use this really fast algorithm to solve problem A as well. So a fast algorithm for problem B implies a fast algorithm for problem A as well. And this other direction kind of shows the other relationship. And in our technique, like our results also follow this kind of technique a little, like it's little more complicated, but the basic principle is still the same. So here we pick a problem whose hardness we either know or we kind of conjecture it to be known, because in complexity theory it's really hard to prove low bounds, like unconditional low bounds. And we reduce this problem A to problem B, and then we conclude a lower bound for problem B using the lower bound for problem A. And as part, we started this project initially with taking problem A as something called the satisfiability problem, and our problem B was these in fact we can these string comparison problems like common subsequence or edit distance. And let me talk about the satisfiability problem. Okay, now again it's a bit what to say, uh, we have this satisfiability problem is like we have input a boolean formula, okay, and this boolean formula has like n variables, and what we would like to know is if there is an assignment that satisfies this formula. And by assignment I mean like would you set say x1 is 0, x2 is 0, like basically you set these variables to either 0 or 1 and kind of check if this that assignment satisfies this formula. And when this formula has this conjunctive normal form, that is, all its variable are connected with this or, and all these clauses which are are connected with an and, when they have this kind of form, then it's called the CNF SAT problem. Okay. And also one more thing is like the in CNF SAT, the clause length is not constrained; it is arbitrary. Now, for this CNF SAT problem, what we know is the lower bound is n, and the current best known algorithm takes almost 2 power n time. And this algorithm just is like searching over all possible assignments because there are n variables. We can have like 2 power n possible like setting to these variables, and the algorithm kind of just checks whether any of these assignment satisfies this formula. And there's this huge gap which people are not able to bridge. Okay? So in 2001, some famous researchers conjectured that there might not be any faster than 2 power n time classical algorithm to solve CNF SAT. And this conjecture became useful in proving lower bounds for many other problems. And uh, for those of you who are interested, you could follow this survey article by Virginia Williams. It's online. And what this article does is it kind of summarizes all these reductions from CNF SAT to various problems. And based on this conjecture that CNF SAT requires 2 power n time, people are able to get lower bound for so many of these problems, which are which was not proven earlier. Now, what we observed is this set conjecture that I talked about. It actually fails in the quantum regime because what did the conjecture say? The conjecture said that we cannot have a algorithm faster than 2 power n to solve CNF SAT. But in the quantum setting, we have something. We have a nice Grover search algorithm, uh, which helps solve CNF SAT in like quadratically faster. That is 2 power n by 2 time. And I will be using this Grover search term again. So I'll just make a mention of that. Now, what Grover search is a very beautiful algorithm. What it does is it can search for a marked item in list of n elements in root over n time, which in classical case requires n. So there's a quadratic gap there. Okay. So now, given that we have this speed up in solving CNF SAT problem, the earlier reductions, the earlier bounds that we get in the classical setting don't hold anymore. Okay, so we thought, okay, let's do we felt it's natural to conjecture that CNF SAT cannot be solved faster than 2 power n by 2 time, even with a quantum computer. And but with that basic Q set that we conjectured, we could only get linear lower bound for LCS and edit distance. And but the current quantum algorithms that are known for LCS and edit distance were still n square. So there was still a gap that we were not able to explain because of this basic Q set. And with further probing, we noticed that these reductions actually encode some more information than just knowing whether there's a satisfying assignment to this formula. It so and something like is there are half of these assignments satisfiable, or say how many assignments in this formula are satisfiable? These are harder problems for a quantum computer than actually uh, just checking whether a particular assignment is there or not. And we kind of use the uh, we hooked on our wood to that direction, and we saw, oh, these reduction actually encodes a property of the satisfying assignment, which is much harder than just checking existence, but kind of less harder than just like counting or majority. And we use the already existing some tools in quantum computing to give to prove the hardness of this property. And using that, we were able to give a non-trivial lower bound of n power 1.5 for this LCS and edit distance problem that was quite open, like it was open for some time. And but we still haven't closed the gap yet, because the best known quantum algorithms for LCS and edit distance are still n square and not n power 1.5. And we are kind of working on that as well to try to see if we can bridge the gap. And but on the positive end, what we saw is we gave linear low bound for orthogonal vectors problem, but which is good, because we have this linear upper bound for orthogonal vector problem, kind of closing this area here, and because this is an optimal low bound. Okay. And then we thought of exploring more complexity results. Like if you see this picture, there are some other key problems like three sum and APSP, which has been explored in the classical setting. And we thought, why not check that in the quantum setting as well. And now this time we picked our second problem as the threesome problem, and we explored these classical reductions from threesome to some geometry problem and finding zero edge weight triangle problem, and we saw what we could do there. Okay. Now I'll give you an idea of what a threesome problem is. This is also a fairly simple problem to express. So we have this list of integers n. We have n integers, okay? And what we would like to know, if there are like three elements in this integers a set, that is a, b, and c, such that a plus b plus c equals to 0. So let's look at this example. In this example, by taking a equals to 1, b equals to 1, and c equals to minus 2, you get that satisfying tuple, triple. And there's another triple as well. By taking a equals to 1, b equals to 4, and c equals to minus 5, you also get a plus b plus c equals to 0. Now, let's look at how this threesome looks in the classical setting first. Okay, so clearly there's a very trivial n cube algorithm, and the n cube algorithm just takes all these settings of all these triples a, b, c from the set. So there are n cube of them, and it checks whether any of these triple adds up to 0. But there's a slightly less trivial but nicer n square time algorithm, and this is how it goes. Now take this set S, make a copy of it, make another copy of the same list. Now make a third copy, but take an additional amount of n log n time and sort the whole list, okay? Now, what you need to do is go through these tuples, like, so because we have like two lists, we have like n square tuples, and check if some of these tuples, any of this tuple, actually is present in the third list with a negative sign. So you're kind of checking for these, whether there's a element in this n square long list, which is negative in this sorted list. So, and the sorting kind of take, like, because you're doing a binary search, you'll take an additional log n time. So what you have here is a n square log n time algorithm. And with another like little slight tricks, you can even improve this algorithm to run in n square time as well, which I will not discuss now. Okay. So now this whole technique we can also use in the quantum setting, but to give a n log n algorithm. How? So you have this list. You've already sorted one of the copy, right? That is, you use n log n time, and then you take these two things again, which need not be sorted. But now you Grover search over these n square tuple. And remember, I told you this Grover search thing is like a search algorithm which works quadratically faster than the classical search algorithm. So here, because we have n square tuple, you have this quadratic speed up. So you kind of get this n log n quantum algorithm for this threesome problem. Now, people had tried to come up with better than n square algorithm in the classical setting, but they put a lot of effort, but there was barely any improvement seen in that area. And they conjectured that threesome requires n square time on a classical computer. And a similar conjecture was also being discussed in the quantum setup, where it's said that threesome requires linear amount of time on a quantum computer, and it cannot be better than that. And um, so a lot of research and people had given a lot of these fine-grained reductions from threesome to many problems like that I've highlighted in gray in the classical world. And we thought, okay, let's kind of get deep down into these reductions and see what it tells us about in the quantum setting. Okay, and the observations that we had were, though depressing, but that will lead to my PhD, so I'm happy about that. And one of the observations that we saw was many of these reductions from threesome to these computational geometry problems or zero edge weight triangle problem, they required sorting the input as an intermediate step. Okay, and we do not have a quantum algorithm for sorting which is sublinear. And because our threesome conjecture in the quantum setting requires that the reductions have to be sublinear, we were stuck there. And so our classical reductions were not directly, like it was not easy to port these classical reductions into the quantum setting. And then we like a little more of brainstorming led us to think and see that we could use these we could use quantum walk algorithm, the kind that Harry talked about in his slide, and show that we could make these classical reductions work in the quantum setting, but that the quantum walk algorithm ensured that these reductions became inherently quantum, and it was not an easy modification of the classical reductions. And using that, we were able to prove, like give lower bounds for these highlighted problems in yellow, and which very nicely turned out to be tight lower bounds, kind of like giving evidence why we have not found better algorithms for computational geometry or zero edge weight triangle finding in the quantum setting as well. And so to summarize what we have done in this project till now is we kind of saw this classical results. That is, like, people came up with this conjecture about CNF SAT taking so much time. Then people came up with this threesome conjecture taking so much time, and they used this fine-grained reduction. So the black arrows kind of indicates the fine-grained reductions in the classical setting, and they came up with these beautiful uh, picture of like which relates the hardness of these problems by basing the hardness of these problems on these major three key problems. And we in our project we are also trying to do we are following the similar principles, but we understand that these conjectures don't hold in the quantum setting the way it used to hold in the classical setting. So we first give the quantum analogs of these conjectures, and we also understood that some of these reductions cannot be directly ported in the quantum world. So we came up with these fine-grained reductions, which are inherently quantum. And we are also establishing this relationships. And I'm sorry, I have to cough. Yeah, we believe our frameworks will help us, close more, like color more of these problems and give lower bounds for them as well. And so, yeah, so this is end of my talk, and I hope by end of PhD this picture is completely quantum as well. And I thank you for the attention, and the thank you for also the opportunity for letting me speak here. Yep.
Thanks a lot, Subha. We're a bit over time, but I think there's time for one question. As usual, raise your hand in the Zoom or write something in the chat. I don't see a question, so let me ask a question. So what exactly are you assuming for threesome? Are you assuming that it takes time n log n on a quantum computer, or it takes time n on a quantum computer?
So we are assuming that it takes time n. And for all the bounds that we get right now, we are ignoring all these polylogarithmic factors.
Mhm.
So that's why it doesn't matter if we think log n or n log, sorry, whether n log n or n, it's
Mhm.
for us the same thing. Yeah.
And you would think that the linear lower bound for such a problem should be kind of self-evident, or is there an issue that the input is given in some quantum realm and therefore sublinear algorithms would in principle be possible, or are not obviously ruled out?
See, it is not because so much of the input, because we have these query algorithms for threesome,
Mhm.
which are sublinear in like it has n power 3 by 4, but uh, but these query algorithms still take a lot of time when we look at the time as the resource. So uh, I don't really know the prince like why exactly it requires n time on threesome. It is more on the literature that we have. It kind of shows that okay, maybe there's no better than an algorithm in threesome.